So, when you picture solving huge environmental problems like pollution, what comes to mind? Probably some high-tech stuff, right? Big filters, complex chemical reactions. But what if I told you one of the best solutions is, well, dirt. Simple, humble clay. Sounds a little crazy, I know, but the science is absolutely fascinating. Let's get into it.
So, could the answer to pollution really be right under our feet? That's what we're going to dig into today. We're going to see how the hidden atomic-level structure of minerals, especially clays, gives them this incredible, almost magical ability to clean up our world. And it all starts with the very foundation of our planet.
You know, when you look at the Earth's crust, it's actually pretty simple. I mean, get this. Just two elements, oxygen and silicon, make up a whopping 75% of it. And when these elements team up in just the right way, they form minerals. These are the real building blocks of our world, and they are the key to this whole story.
All right, here's what we've got on tap. We'll start with the basics, Earth's building blocks. Then we'll dive into the secret life of clays and uncover their amazing cleaning superpower. We'll see it in action with some real data, meet a superpowered cousin called zeolites, and then, to keep things balanced, we'll look at a mineral's dark side.
Okay, first up, Earth's building blocks. So what is a mineral, really? I mean, it's not just some random rock. And getting this definition right is super important, because a mineral's specific atomic blueprint is what decides if it's going to be a hero or a villain in our environment.
So here's the official definition, but the part you really need to zero in on is this: characteristic internal atomic structure. Just think of it like a specific Lego model, but on a microscopic scale. It's that unique repeating pattern of atoms that gives every mineral its special powers. You know, what makes a diamond super hard or what makes talc super soft.
All right, let's meet our hero, the clay mineral. Clays belong to this bigger family called phyllosilicates. Fancy word, but all it means is they have these cool sheet-like structures. And inside this family, there are a few key players you've got to meet.
So we've basically got three main clans of clay: the Candanites, the Smectites, and the Illites. And the big difference between them all comes down to their atomic structure, which scientists call TO or TOT. Now you can just think of it like a simple sandwich. Let's actually look at what that means.
Okay, first up, we have kyolinite. This is a candelate clay. See that simple TO structure? It's like an open-face sandwich. You've got one T layer stuck to one O layer. And these layers are stacked on top of each other pretty tightly, so water can't really squeeze in between. That makes it what we call a non-expanding clay.
Now, check out a smectite. Totally different story. This one has a TOT structure. So this time, it's a full-on sandwich, right? You've got an O layer squished between two T layers. But the bonds holding these sandwiches together, they're super weak. And that means water can just flood right in and shove the layers apart. It's why these guys are famous for being expanding clays. They can swell up like crazy.
And last but not least, we have illite. Now, it also has that TOT sandwich structure, but there's a critical twist. See those big potassium ions? They're wedged in between the layers, acting like these little pillars. They hold everything together really tightly, which stops water from getting in. So even though it's a TOT structure, illite is another non-expanding clay.
Okay, so we've got expanding and non-expanding clays. Cool. But how in the world does that help clean up pollution? Well, the secret isn't just about sucking up water. It's all about electricity. This superpower actually has a scientific name: cation exchange capacity, or CEC for short. And here's the simple version. Clay surfaces naturally have a negative charge. And you know what they say about magnets: opposites attract. This negative surface can literally grab and hold on to positively charged ions. And guess what a lot of pollutants like heavy metals are? Yep, positively charged ions.
So you're probably wondering, where does this negative charge even come from? Well, it's mainly three things. First, sometimes in the crystal structure, a lower charge atom swaps places with a higher charge one. Second, sometimes there are just little imperfections, like missing pieces in the atomic Lego build. And finally, you get these broken bonds right at the edge of a clay particle, and those create negatively charged spots.
So when you add up all these little atomic quirks, what do you get? You get a powerful net negative charge. And that right there is what turns a tiny clay particle into a molecular magnet, perfectly designed to pull pollutants right out of the water.
Okay, this molecular magnet idea sounds awesome in theory, but does it actually work? Like for real? Well, let's let the data do the talking.
Yeah, this is the big question, isn't it? How well can these little magnets actually trap nasty stuff like lead, cadmium, or copper floating around in our water? Let's take a look at the evidence.
Okay, so these graphs are called adsorption isotherms. Fancy name, but they show us exactly what's happening. Adsorption, with a D, is basically when stuff sticks to the surface of something else, kind of like static cling. Now look at how that curve just shoots up and then flattens out. That steep climb, that's the clay furiously grabbing those metal ions out of the water. Then it flattens because, well, it's starting to get full. It's a perfect picture of that molecular magnet in action.
And this chart makes it even clearer. Along the bottom, you've got how much clay was added, and up the side, you see the percentage of junk that was removed. I mean, the connection is crystal clear. The more clay you throw in, the cleaner the water gets. You can get up to removing pretty much 100% of the metals. It's just, wow.
Clays are amazing, no doubt about it. But they aren't the only minerals with this cleaning superpower. It's time to meet their even more powerful cousins, the zeolites.
So while clays have that 2D, sheet-like structure, zeolites have this complex 3D framework. Think of it like a microscopic sponge, just riddled with tiny pores and channels. This gives them a massive internal surface area and an insanely high cation exchange capacity. I mean, look at these numbers. They're way higher than most clays. And that's exactly why zeolites are such commercial powerhouses. You'll find them in everything from your water softener at home to major industrial cleanups.
Okay, so we've seen how a mineral's structure can make it a hero. But for the full picture, we have to look at the flip side. A mineral's unique structure can also make it incredibly dangerous. And for that, we have to talk about asbestos. So these are some of the minerals that we group together as asbestos. Now, just like clay, they're silicates. But instead of that sheet-like structure, these minerals grow in a very specific, fibrous, needle-like shape. And that shape, well, that shape is the key to both why they were so useful and why they are so deadly.
And here's the tragic irony of asbestos. The very things that made it a fantastic insulator, that strong, fibrous shape and its resistance to breaking down, are the exact same things that make it so dangerous to us. When you breathe in these tiny, durable fibers, they can get stuck deep in your lungs, and your body just has no way to get rid of them. And over time, that can lead to horrible diseases, sometimes decades down the road.
So it really all comes down to that atomic structure, doesn't it? The same basic rules of chemistry that can create a life-saving molecular magnet in clay can also create a life-threatening needle in asbestos. It's just such a powerful reminder that some of our biggest problems, and maybe some of our best solutions, are literally right there in the ground we walk on. It makes you wonder, right? What other secrets are still hiding, just waiting to be discovered, right beneath our feet?